Hello and welcome to this next lecture on machine learning. In today's lecture we will further build upon the perceptron, discuss kernel perceptron and conclude with a variant of perceptron called the sigmoid perceptron or logistic regression. So recall the perceptron update rule. The basic idea for a two class problem was to look at the unsigned distance of a point from the separating surface. This was the unsigned distance y w transpose phi x, and if you find that the unsigned distance is negative, then something wrong. So recall that we are interested in classifying between positive and negative points, and the separating surface is characterized by the normal w, and the unsigned distance is supposed to be positive for points on either side. The signed distance, as the name indicates, will change its sign across the separating surface, but that is not expected from the unsigned distance. So the key here is misclassified points have negative unsigned distance. So in such a case you basically update the weight vector, and the update is proportional to the feature vector at that misclassified point multiplied with y. You optionally also associate an eta. This eta is referred to as the learning rate. So the larger the value of eta, the larger the updates. And we also discussed the intuition behind the update. Following this update, we expect that the unsigned distance with respect to the new separating surface is more positive than the previous unsigned distance. So there is chance or more hope that this point is classified correctly now. So again, illustrating through the example, we pick or any of one of these points which have negative unsigned distance. We chose this point, and depending on the learning rate eta, we would find a corresponding shift in the separating surface. So yes, it got significantly shifted. Perhaps eta was large enough. We find the next point that is misclassified, further update, and we have a separating surface. We will provide the error perspective to this perceptron update rule. So perceptron update was to explicitly account for the signed distance of misclassified points from the hyperplane, and the signed distance is of a point from the hyperplane is w transpose phi x. The unsigned distance is basically y times w transpose phi x. So if w transpose phi x and y share the same sign, which is how it should be, this indeed is a magnitude of the distance. So unsigned distance ideally, which means if a point is correctly classified, is magnitude of distance. And as I said, ideal here corresponds to correct classification. On the other hand, if you do not have the ideal situation, that is misclassification, in such a case the misclassification cost for a point x is minus y w transpose phi x. So we are trying to keep this quantity positive, though it turned out to be negative, but now we call it a cost. So cost has this negative sign, but it is supposed to be positive for misclassified points. We also will refer to this as the error associated with point x. So Ex is minus of y w transpose phi x. Now if you sum the misclassification cost across all the points, which is sum Ex over all the misclassified points, this is only restricted to misclassified examples, then you overall get the misclassification error. The idea behind perceptron update is basically to try and minimize this misclassification error. If you apply gradient descent, it's also called batch perceptron algorithm, you will need to take the gradient of E at a particular instance of time with respect to W. So please note that the set of misclassified points can and will change across iterations. So this is a simplistic assumption that the points remain the same. If you take the gradient, you will have summation over the same set of misclassified points of y times phi x. The gradient descent rule is then wk plus 1 is wk minus the gradient times the learning parameter, and that turns out to be eta times sum over misclassified points of y times phi x. This is not completely correct because the error minimization is actually a combinatorial optimization problem, and we have kind of fixed the set of error points. So not completely appropriate for a combinatorial error minimization problem, which is our case. In fact, it is possible that if you were to update the weight vector for a single example which is misclassified, a whole bunch of other misclassified examples might land up being correctly classified. So instead of considering all misclassified points simultaneously, how about an approximation? How about being stochastic in the update, which means consider the error function and the gradient of the error function as a sum of the gradients of the error function computed for each point. And instead of taking the gradient of the entire error function, take the gradient with respect to that specific point, any of the misclassified points. So this is gradient descent for that specific point, which means you are trying to minimize the error incurred for a specific misclassified point. This is basically our perceptron algorithm. So this gives the error minimization perspective for perceptron update. Is the perceptron update rule guaranteed to converge? So we will prove the following. If there exists an optimal separating hyperplane with parameters w star such that for all points the unsigned distance is indeed non-negative, then the perceptron algorithm converges. So all we are saying here is that there is proper separation of the negative points from the positive points using the completely separating surface, which is characterized by the normal w star. We would like to show that eventually the wk plus 1 comes arbitrarily close to w star, and we are going to measure this closeness modulo a scaling factor rho. So all we want is that this rho is constant or independent of iteration number k. It may not be constant with respect to the learning rate eta. How do we do this? Well, first we decompose this wk plus 1 minus rho w star into two parts. The first component involves the distance of the previous iterate from rho w star. So rho remains the same, and basically if you now expand the squares, you will get wk minus rho w star square plus a bunch of other terms, square of y phi x and 2y times wk minus rho w star transpose phi x. Okay. And this was all for a misclassified point phi x. So remember that phi x was misclassified. So remember that x comma y was such that wk misclassified it. So for convergence of perceptron, we need the left hand side to be less than right hand side at every step, and it is desirable that it is less by some constant value, again which is independent of the iterations. So this constant theta square should be independent of k. We are basically ensuring that there is a finite decrement in every step. What is the implication? Well, if this were true, we could characterize a number of iterations in which we will converge. So if we ensure 4, we can basically ensure that the number of iterations for convergence is order of w0 minus rho w star square divided by theta square. Now what is a desirable theta square? Well, we have already seen in 2 that wk plus 1 minus rho w star square is wk minus rho w star square plus some terms. So those additional terms that came from 2 should be less than equal to minus of theta square that we have got from 4. We will post a tutorial with some problem 4, where we will discuss more about the number of iterations required for convergence. Well, we will now discuss why convergence will hold in the first place. We will make the following observations. First of all, as already pointed out, x comma y was misclassified, and therefore this unsigned distance should be negative. This is with respect to w from the kth iterate. Related to the first point is also the fact that w star should classify all the points correctly. Wk didn't, but w star will, and since w star did, we could consider the distance of the closest point from w star. So let us again depict this pictorially. So let us say these were the negative points, we had some positive points, and let us say this was a separating surface characterized by w star. Now there will be some point which is sufficiently close to the separating surface. Let us identify this point to be the closest, and it has a corresponding distance. I am going to call this distance minus delta. So delta is nothing but minus of min over all the data points of 2yw star transpose phi x. So minus of the smallest distance. Of course, there is an additional factor 2y, so I will just go ahead and call this smallest distance minus of 2y delta. So but this minus of min is the same as max of the minus. So now what can we say about delta? Well, we know that the points are separable linearly, which means that delta, which is the negative of the shortest distance, should be certainly less than 0. We will also assume that the points are lying bounded within a sphere of finite radius. Let this radius of the sphere be gamma. So gamma is the radius of the sphere. In fact, we have defined this gamma square to be max over all the points of phi x square, norm of phi x square. It is a Euclidean sphere. So we have already seen that since the data is linearly separable, delta should be less than or equal to 0. So making the required substitutions, we will get that wk plus 1 minus rho w star square is less than wk minus rho w star square plus gamma square, which is the upper bound on phi x square, norm phi x square, and rho basically came from our rho w star. The delta is what we get by looking at minus 2 y w star transpose phi x. There was an additional term minus 2y wk transpose phi x, but this is already known to be less than 0. So as a result, we can ignore this. Is there a rho for which we can get a minus theta square that is independent of the iteration number? So question is there a rho value such that gamma square plus rho delta becomes equal to minus of theta square? So note that delta was less than 0, gamma square is positive. So we would like the rho to make the left hand side dominantly negative, and indeed we can do that. We need to take rho such that gamma square plus rho delta becomes less than 0. That is, we would like rho delta to be less than gamma minus of gamma square. Now note that delta is negative, so this division by delta would mean inequality gets flipped, and so you will get rho greater than minus gamma square by delta. So any rho greater than minus gamma square by delta should serve the purpose. So we will take rho to be 2 gamma square upon minus delta, so we just doubled. So this basically will lead to a value of minus theta square as minus gamma square. So theta square is gamma square. So wk plus 1 minus rho w star square for this specific value of rho decreases by at least gamma square at every iteration. So here is a summary: wk converges to some rho w star by making a minimum gamma square decrement at each step. That means we get convergence. We can further prove that the number of iterations for convergence cannot exceed gamma square by delta square, where delta is the smallest unsigned distance of a point to the separating surface, and gamma square, as before, is the radius of the bounding sphere. Can we come up with a non-linear version of the perceptron we just discussed? How about kernelizing the perceptron? And indeed, it is possible to recall our discussion with non-parametric regression. Very similarly, we can actually set the decision function to be summation over all the points, some weight associated with each point, alpha I times yi times a similarity between x and xi. This could be imagined to be the basis function centered at xi and evaluated on x. We can have this optional offset parameter b. Now for this kernelized perceptron we can show that there is an algorithm that converges. We initialize all the alphas to zeros, and for all the points on which there is misclassification, so if xi yi is misclassified, what we do is update the weight for xi, but here the update is very simple, so alpha is incremented by 1, but one can show that this increment of 1 in alpha space corresponds to the yi times phi of xi update in the space of features phi. So one can similarly analyze the convergence of kernelized perceptron, and this will be left as a homework problem. In fact, the tutorial problem in 6th tutorial will actually correspond to proving the convergence of the kernelized perceptron. One can also get nonlinearity in perceptrons through neural networks. Neural networks are cascades of layers of perceptrons, so you have input that goes to a perceptron. Perceptron does a thresholding, hard thresholding 0 1, this is based on sign of the input. You take this input and maybe some other similar sign inputs, pass this through another threshold, and so on. This gives you nonlinearity. However, learning is challenging with such nonlinearity, which is because of its non-differentiable nature. What we would like is to deal with an error that is not combinatorial, that is deterministic with respect to the error points. So what we would like is learning with differentiable perceptron function. Is there a way that we can approximate the sign function, which is plus minus 1, abruptly plus and abruptly minus 1? Can we approximate this using a smooth variant? In fact, that is the basis of the sigmoid perceptron or logistic regression. The sigmoidal perceptron classifier, or also called logistic regression classifier, is a single node perceptron like classifier where the sign of W star transpose phi x is replaced with some other function g of W star transpose phi x, where g is a sigmoid function and gs is basically 1 divided by 1 plus e raised to minus s. There is a slight rescaling here because 1 upon 1 plus e raised to minus s is always going to be in the range of 0 and 1 that we point out here, it is in 0 and 1. So we are going to assume that y, which was earlier plus or minus 1, is now going to be either 0 or 1. Earlier we had a version of y which was basically plus 1 or somewhere down here minus 1. So this is a bit of readjustment, but other than that we have actually got a very smooth differentiable decision function g. So one can also interpret this smooth function as probability. So as pointed out here, g of W star transpose phi x, which has this form 1 by 1 plus e raised to minus W star transpose phi x, can be interpreted as probability of y equals 1 given x. In fact, this is nothing but treating the y as a Bernoulli random variable, but for a very specific value of the Bernoulli parameter. This is the probability of y equals 1 given x, which is the probability of heads. The probability of tails, or probability of y equals 0, is nothing but 1 minus the same, 1 minus probability of y equals 1 given x, and this is e raised to minus w star transpose phi x divided by the same denominator 1 plus e raised to minus w star transpose phi x. One can estimate the w hat for the separating surface using principles of optimization that we have already discussed for probabilistic models. We will actually resort to the maximum likelihood estimator. It is the estimator w hat that maximizes the likelihood dw of the data. It assumes that all the instances phi x1 to phi xm of the data are independent and also identically distributed. So under this assumption one can actually write w hat, the maximum likelihood estimator, as one that maximizes the likelihood, which is written as product over all the examples I equals 1 to m of probability of yi given xi and w. Now yi could be 0 or yi could be 1, so one could look at probability of getting a 1 given xi comma w, but this should be instantiated if yi is 1, so I just exponentiate this with yi. On the other hand, it could also be probability of 0 given xi and w. This is of course mutually exclusive from probability of 1, and therefore I am going to exponentiate this 1 minus yi. So if 1 minus yi happens to be 1 or yi is 0, you get this term, else the other one. So expanding this, we basically get some of these exponentiated products, product of these exponentiated terms. One can further abbreviate by adopting a decision function notation. Fwxi is the decision function and 1 minus Fwxi is 1 minus the decision function. Basically this corresponds to the probability of 0 given xi and w, this corresponds to the probability of 1 given xi and w. One could also employ the standard tricks for likelihood by minimizing the negative log likelihood, and I have also put in a minus 1 by m here for normalization and actually cancel out, getting it to some standard scale. You can derive the expression for EW, and it turns out that EW is a very interesting form called the cross entropy function. Minimizing this cross entropy function amounts to maximizing the original likelihood. So this cross entropy is actually a loss function. More about this in the next class. Thank you.